very excited to learn from your extensive experience in technologies for water treatment, especially your dialogue on new innovations in water treatment. I hope it can better inform our understanding of the relationship between treated water and clean hydrogen production. Given your role as the Regents Professor in the School of Sustainable Engineering and the Built Environment at ASU, and your position as the Fulton Chair of Environmental Engineering, your perspective on integrating innovative and sustainable water treatment practices in support of Arizona's growing clean hydrogen economy is incredibly valuable. So, like I said in the email, I'm going to base a lot of the questions on just a few of your papers. And many of your publications focus on desalination and water treatments for clean hydrogen production. Although clean hydrogen typically uses less water than certain types of electricity generation to produce the same amount of energy, it's crucial for clean hydrogen developers to prioritize efficiency and consider local water availability. As we explore the role of clean hydrogen in contributing to a carbon neutral economy, I'd love to discuss both the potential and the challenges regarding water treatment, especially with regards to how this can affect how hydrogen production might unfold in Arizona. And I'm excited to hear about your thoughts on how Arizona is gearing up for these changes, especially from an engineering and technological perspective. So for my very first question, you joined ASU in 1995, almost 30 years ago. During your career, you have made significant contributions to water quality and treatment research. Given your extensive background in education in civil and environmental engineering, can you share what drew you to this field initially?
So yeah, 1995 was a long time ago. But I remember a few things when I first joined. One of them is I went to listen to this wacky professor from Germany give a seminar in physics as a special lecture, and he talked about a hydrogen economy was just around the corner. And so that was in 1995, so many corners ago. And so I think fondly upon it, and sometimes I think, why didn't it happen? At the same time, we had projects funded by large petrochemical projects. That this was all when the Kyoto Agreement was being negotiated around CO2. And in the end, it didn't get adopted or ratified in the United States, so things changed. In the late 1990s, there was a lot of interest in petroleum companies to do novel things. This is kind of when light work started, and we were doing work on photosynthetic, the algae and bacteria to produce fuels and do great things. But somehow the momentum around hydrogen kind of changed. So my traditional area is on water treatment, but I thought about hydrogen a lot. And so in the early 2000s, I partnered up with a guy in mechanical engineering, Jonathan Posner, who did fuel cell research. And I said, geez, you use all this hydrogen, but like, can't we make water from it? And so we ended up getting some projects funded. We published some papers looking at if you brought hydrogen to Arizona from somewhere, could we use it in a fuel cell and react with the oxygen that's here and make water? So we did a number of things. It was just kind of like what they used to do on the Mir space station. And sure enough, we could make water. We looked at the quality of the water and how things like the proton exchange membranes in there degraded, and actually that's like fluoride in the water and things. So, there were some challenges, but it was definitely doable. But one of the proposals I wrote got funded from this a Water Research Foundation, because I think I made the case that this was going to impact local water. And it started out with actually a dialogue between a water buffalo, which is kind of what they call people who do water in the Southwest, and a Canadian Monty. And, they were going back and forth saying, hey, the water buffalo said, why don't you, send us hydrogen? You have a lot of water, you can make it with hydropower, it can be green, and, and this will allow us to have hydrogen in Arizona. And they went back and forth, and the Canadian Monty said, well, you're stealing our water. Right? So that's how they would ship us the hydrogen. So I've been thinking about this for a long time, and now we have companies who are going to think that the hydrogen economy is around the corner, and they want to use green energy, but not hydropower in Arizona, but solar power. And so, if you use solar power, you need to split water, and you need to get water from somewhere to make hydrogen. So roughly it might take 50 or 60 liters of water to make a kilogram of hydrogen. Now, where's all that water going to come from to harness the solar energy? And I think that's where we kind of started, stepping in more recently to kind of think about, what alternative water sources could we use for that. And at the same time, we have a startup company funded by NASA to look at hydrogen production in space. And so in space, it's a little different than on Earth, but it's a closed environment. There's no rain, there's no rivers, and you have to recycle all the water. So it comes back to the same idea of using water to make hydrogen. And yeah, I care less about the hydrogen that you make, but the fact that you're making hydrogen means you left behind pollutants and salts. So actually making hydrogen can be viewed as a way to purify water. So it's kind of come full circle over those 30 years. Sorry, it took a little while to get there, but that's kind of how my thinking around hydrogen has been occurring.
That's so, because that's so interesting, especially the last thing you said about how purifying water, making hydrogen can be viewed as a way to purify water. So that's a really good way of connecting everything. I find it very interesting. What motivates your continued research in water treatment and emerging pollutants?
So, we're walking bags of water, we're greater than 70 or 80% water, so we need water. And when I moved, I grew up around New York City, but when I moved to Colorado first and then Arizona, I kept getting drier and drier. Thought I was only going to stay here for 2 years because there's not a lot of water. What would I do here? But it turns out water is really important here. And so to me, it's really easy to talk about water, but just kind of non-professionally, I like snow and skiing and snow sports. I like fly fishing and walking in rivers. So a lot of the things I do, I actually like water just in addition to needing it every day. So, our students have done everything from kayaking and boating in different rivers and creeks around Arizona and other places to studying water in China and Africa and even Antarctica. So it allows me to go lots of places I'd like to go.
I think it's always best when we can combine our professional passions and our personal passions. So I'm glad that you managed to find that mix for your career. In one of your most recent papers that you co-authored titled Ultra-Fast Green Hydrogen Production from Municipal Wastewater by an Integrated Forward Osmosis Alkaline Water Electrolysis System.
It's a mouthful.
You discuss how recent advancements in using renewable energy for seawater electrolysis have shown promise for green hydrogen production, but they face challenges with slow power to hydrogen conversion rates. Your research introduces a system that combines forward osmosis for water extraction with alkaline water electrolysis, known as can you correct me, the FOSA system?
Sure, but it's everyone needs an acronym, and if our title didn't have ultra fast hydrogen production, what would it say? Slow hydrogen production? I mean, right? So you have to get people's attention, and so part of this was about showing that this one alternative water source that people think of as a waste sometime, and that's wastewater, can be used to make hydrogen, but in the process you clean the water, right? So there's a lot of things that got linked together in here. The first is can you use seawater to make hydrogen? The answer is yes, right? So we've been working with a Japanese group for a while just on solar photolysis or water splitting, and you can use seawater. But for electrolysis, typically the chloride, seawater is very salty, a lot of chloride, it forms chlorine gas, and that degrades the electrodes. That's in the electrolysis part. So there's an anode, a cathode, if you remember back. And so it's at the cathode where you make hydrogen. So it turns out there's chloride in the water. You make chlorine gas, and it's a very, just like bleach, it's an oxidant and degrades those electrodes. So the typical way people would do it is to take seawater and pass it through reverse osmosis. That takes energy, and then use the clean water that comes out and without any fluoride. And on the big scheme of things, that works. It's a way to make hydrogen. Less than about 5% of the total hydrogen cost would be, this desalination cost. And the funny thing is, I was partnering with people on this in Hong Kong, where they have a lot of wastewater from all the people that live there, but also a lot of seawater. But it's really, they dump this, wastewater into the ocean, and there's risks associated with it. But wastewater has less salt than seawater, and so we wanted to see how we could use this waste stream instead of seawater. And I was interested in partnering them because in Arizona, if you didn't recognize it, we don't have any beaches, right? There's no ocean, nearby. So we would have to import water huge distances if we wanted that as our water supply. So I was really interested in exploring this technology to take wastewater and use it for hydrolysis or water splitting to make hydrogen. And so the technology in there, so reverse osmosis, you add pressure, you squeeze clean water out of salty water under pressure. So forward osmosis is a little bit more like how a tree works, right? So you have a tree as a membrane, and water gets sucked across the membrane into the kind of phylum of the tree that goes up the tree. And so the reason water moves across that membrane is one side inside the tree is pretty salty, right? It's high conductivity from things like organic acids. And so if I have a low salt and a high salt, water wants to dilute the high salt. So it'll move across a membrane. So in this case, this is called engineered forward osmosis. So we put potassium hydroxide, a common salt used in alkaline hydrolysis, to pull clean water across the membrane. So it leaves all the nasty stuff in wastewater behind and only moves clean water from a wastewater, pretty low salt, to a high salt, this potassium hydroxide, to create this alkaline water hydrolysis, which is a really common commercial way of making it. So all you need to do is that the rate of water evolution to oxygen and hydrogen has to equal the rate that clean water moves across this membrane. So those were like the 2 or 3 key insights in there, is that this potassium hydroxide that people are already using for hydrolysis is a good draw solution. It pulls clean water across these forward osmosis membranes. So that's, why a lot of these are in there. Now, is it good for Arizona? Well, we already reuse a lot of our wastewater, but not all industries do, or they want to. And it becomes very energy intensive for them to get rid of their wastewater. So, a big water user currently is all these semiconductor manufacturers, and they make a lot of industrial wastewater that they currently get rid of by evaporating the water, but they reuse a lot of it internally in different things. But in the end, they need to evaporate more water, and it's very energy intensive. So we think they could use processes like this, make hydrogen from the industrial wastewater, more so than, say, the wastewater that you flush down the drain.
No, you inadvertently answered my next questions, was basically
okay.
Yeah, what impact would the implementation of your system at the city scale have on further improving Arizona's already sophisticated wastewater utilization? So you did that. And
and then I think it depends what we do with that hydrogen, right? If we put it in a truck, right, to move around things, we'll lose the hydrogen into the atmosphere, which is fine, it's clean. But if we run, say, fuel cells and different things, let's say we try to store solar energy from the summer as hydrogen to use in the winter when we don't have as much sun. But if we recover that hydrogen to, say, run a fuel cell, then we can grab oxygen from the atmosphere and make it clean water again, right? So it all depends how we use the hydrogen, that we can actually, kind of recycle this clean water multiple times in making hydrogen and using hydrogen, if we think about how to use it.
Thank you.
So I look at all this, I look at all this from the water point of view, not from like the energy hydrogen viewpoint.
Thank you. That answers my second part of the question, which was what effect could this have on supporting the development of a clean hydrogen economy? So thank you.
Yeah.
Just moving on to the next question. So in arid regions like Arizona, using alternative sources like treated wastewater or desalinated brackish water can help reduce reliance on fresh water for hydrogen production. In a paper you co-authored called The Potential of Electrodialysis as a cost-effective alternative to reverse osmosis for brackish water desalination, it's discussed how the levelized cost of water is a crucial factor in determining the viability of water treatment technologies. Your study highlights that electrodialysis can have a lower levelized cost of water than reverse osmosis across, to quote, the entire brackish water salinity range. So my question is, considering that Arizona has over 600 million acre-feet of brackish groundwater, can this brackish water be directly and more economically purified through electrodialysis rather than reverse osmosis? That's just my first part.
So I think, yeah. So I think it can play an important role. So reverse osmosis is a more mature technology. So electrodialysis can be cheaper per gallon of water, per acre foot of water. But the real advantage is you have the opportunity to do what's called selective electrodialysis. So reverse osmosis removes all the salts. And you can do things within electrodialysis to be selective. So we can remove sulfate and calcium, but maybe leave some sodium and chloride in there. And that has a bunch of advantages. One of the biggest advantages is if you take salt out of something, you have to get rid of it. And so one of the advantages of electrodialysis, when you look at kind of the whole process, is what do you do with all that salt that you remove from the salty groundwater? So in the Phoenix area right now, a lot of it's going out to Palo Verde nuclear power plant where they evaporate it. So I think there's niches and ways to compare electrodialysis and reverse osmosis, but they're very different processes. Similar, they have membranes. One operates under pressure, one operates under an electric field. And so there's some thought on making electrodialysis since it operates off of DC power, solar powered and things. So there's a number of different advantages, but I think as a platform, it just hasn't developed commercially as much as reverse osmosis. So I think you'll see RO a lot more, even though the theoretical costs are cheaper. It takes technology development and demonstration to convince cities to invest money in a technology that might be less proven. So what we're trying to do in some of our research and centers is to help fill that kind of technology demonstration gap in the field in Arizona to show how these things could be more effective.
I guess that answers my next question, which was how likely is it that this technology could affect water availability for clean hydrogen production, which is just right now, it's too early to say. It's in a very nascent, it's an development structure, a system.
So they're commercially available. They're just not widely used. And, anytime a technology comes along that's used in a geographic area and it doesn't work quite as people wanted, they tend to look at it in a bad way, kind of like a movie gets, some Rotten Tomato rankings, right? It doesn't mean it's a bad movie. It just means somebody didn't like it. So I think, for the large scale hydrogen manufacturing that's moving to Arizona, they're planning to use reverse osmosis because it gets them a proven level of water quality that they're a hydrogen producer, is not a water treatment company, although maybe they should be, but they're not. Right? So they think of the water as the commodity, whereas people like me think of water as the product, hydrogen as a commodity. So I think you could definitely use electrodialysis or all its different versions to address brackish water, and I think in the end could have some big advantages to reducing the cost of hydrogen production. But the hydrogen company, again, treating the water is less than 5% of cost. Most of it's the energy to make the hydrogen on their electrodes. So they don't want to take the risk on something that isn't a major cost factor for them.
Okay, thank you.
Mm.
So in the paper that you co-authored called The Minus Approach Can Redefine the Standard of Practice of Drinking Water Treatment, your research introduces the minus approach as an alternative to conventional chemical-based water treatment. Can you explain what the minus approach entails and what potential benefits it has for improving water quality and safety?
Yeah, so kind of the Victorian age way of treating water, which treats most of the water in Arizona and around the world, is you add chemicals. So you add alum, and it's aluminum salt. You add chlorine. You add um, you know ammonia. You add acids. So you add a lot of chemicals to treat the water, right? So that's not removing things or minus. It's the additive approach of doing it. And it turns out that leads to all types of consequences. So when I put these things in water, like these aluminum salts, yes, it removes things, but it actually forms a lot of sludges, aluminum solids, sludge like mud, and it gets disposed of to a landfill. So, you've added these chemicals, but yet you end up putting them in a landfill. They do work, they purify the water. And if I add chlorine to water, it does kill pathogens, which is good, but it also reacts with things to form chloroform, things that are carcinogens, right? So I add a chlorine, it does some good, but it does some bad. And so people have always been trading those things off against each other. So that's a conventional kind of way. The minus approach is changing the technologies from Victorian age to more modern technologies, where I take things out instead of adding things. So, for example, instead of adding this alum to remove particles, and then making a sludge with the particles in it, I put in a membrane where the particles are rejected and without adding any chemicals. If I have organics in the water, instead of trying to add more and more, oxidants to destroy them, I can absorb them onto activated carbon. And I can use UV light instead of chlorine, right? So all these things avoid adding more chemicals to water. So the minus approach is taking more things out than you add to the water. And in the end, if we had done this in the 1970s, actually the water today would be much cleaner. So you can make the water much cleaner, much more, lower risk, by removing things instead of adding chemicals to remove other chemicals.
Thank you. Just to clarify, is this a new approach that you and your colleagues have thought of, or are you building on earlier minus
Sure.
approach?
So the water treatment industry is very conservative, right? So you build big things. It's like building a highway. You're not going to build a highway and 5 years later rip it out and put in a new one. You're going to keep adding on ramps and off ramps and widening it. So that's what they do in water treatment. These are big public works projects. So it's hard sometimes to, in a pretty conservative industry, because it's paid for largely through taxes and water bills. It's not like selling something on, Amazon or some other commercial site. These are mostly public service types of things. So people want to keep prices low and affordable for water. So it's hard sometimes for people to take their head out and look at the broader picture. I'd say that this minus approach is the trend that's been happening over 10 or 20 or 30 years, but people haven't thought of it that way. They've tried making hybrids of different things. But I think in Arizona, you talked about wastewater. So we reuse wastewater, is a pretty new endeavor. And there, they fully embrace this minus approach concept. You take more things out than you add chemicals to put in. But as we were writing this, we had authors from Europe, and they think about things much differently in Europe because they're an older civilization than we are in terms of how long they've used river water. So they've also integrated more of this minus approach thinking. But sometimes you need to write a paper to tell people, look what great things you've been doing, And if you thought about this more deliberatively as you expand your infrastructure, instead of just making more of the same, let's think about making things that, follow this minus approach. It could save money, it could reduce the size of the facility, and in the end, make better water.
That's really interesting, and I'm looking forward to seeing how our water treatment can evolve in the future.
Yeah.
In your reaction art.
I'll give you just one example. So you said I've been here a long time. So I've been here a long time. And in the water area, things have moved slowly. But when we started here, they were very conventional plants, and people started adding powder activated carbon like charcoal into the water whenever the water smelled bad. And now they've stopped doing that. And now they follow the minus approach, and they use, filters that are filled with a special type of charcoal that remove regulated and unregulated chemicals. And this started one city at a time, but now pretty much the whole metropolitan Phoenix follows the same approach. So some of these are kind of evolving trends.
Thank you for clarifying. In your reaction article that you wrote, Avoid Fairy Dust When Engineering Water Purification Technologies, you mentioned the potential of engineered metamaterials to improve water treatment processes. Can you explain metamaterials and some examples of their application?
Well, do you know what fairy dust is?
I read the article a couple of times. Was it the nano? was it the nanomaterial?
Yeah.
Okay.
So, we have a center funded by the National Science Foundation called the Nanotechnology Enabled Water Treatment. And early on, people wanted to throw nanomaterials as like fairy dust into water, and it would do all these wonderful things. So that's not the minus approach, is it? Like adding something to water to get something out. Because then I need to get all the fairy dust out, because it turns out the fairy dust isn't good to drink either. And I need to get every fairy dust particle out of the water. So it actually makes it like harder to treat, not easier to treat. So one of our key observations is following this minus approach is that we ended up putting nanomaterials on surfaces, but maintaining their really novel properties. Some nanomaterials are electrically conductive. Some, interact with light. Some have really high absorption capabilities. They do really interesting things, but you would have to attach them onto surfaces. So if I just glue a particle on a surface, hopefully it doesn't come off, but then it's just a particle on a surface, right? I haven't really made it, better. And it is the minus approach. Things come by, get purified and come off. But a metamaterial would be, that nanomaterial on a surface, like inside of a little house, right? Inside of like a cavity, for example. And only the chemicals that you want can get into the cavity, but not the ones you don't want. So what do you want coming into the cavity would be a chemical pollutant, maybe some, chemical that was used in Las Vegas that got into the Colorado River that comes here, right? So, we want to destroy certain types of chemicals, or maybe we want to convert nitrate from agricultural water into a benign byproduct. So the surface of this nanomaterial is reactive. It's sitting inside of a cavity where things can come in and out, but it prevents things that would, inactivate the nanoparticle, like calcium. So things that would inactivate the particle are excluded. So a metamaterial is something that has both a structure and a functionality that are synergistic with each other. So fairy dust is not good. That's not the minus approach, right? So attaching things to a surface makes it more the minus approach. And a metamaterial gets synergy between, say, the nanomaterial activity and what you're attaching it to.
Thanks so much for explaining. Definitely a high-level paper, and I just wasn't quite clear on the metamaterial. So thank you so much for clarifying that for me.
I have to say, there's all types of definitions, and if you look in material science, there's things. But the thing that really got me thinking about this was a guy at the Technion University in Israel, and his name is Benjamin Palmer. He's a biologist. but he was talking about photonic nanocrystals and how these two-dimensional things let lobsters see in the deep ocean. And so it turns out that like they adjust these lenses, these nanomaterials in the lobsters, optical receptors to concentrate the light to another receptor. So it's a really cool example of like a biomimicry or naturally, engineered or naturally occurring metamaterial. And so we're trying to do very similar things with light to purify water from an engineered perspective.
That's very interesting. Especially I have a background in marine biology as well, so I thought that's absolutely very fascinating.
Oh, you got to look up this guy Benjamin Palmer. Okay. So, and these photonic nanocrystals, there's like a really cool history behind it.
I will. That sounds very interesting. How do you envision these materials transforming the field?
Right. So, the field of water treatment, there's the water that you drink, right? But, as being part of society, we need water to make computer chips. We need water, to wash our wounds at the hospital. We need, water at the, to clean, the airport, right? So we need water for lots of things. So the approach in the past, as you've been to pretty much, treat all the water that a city gets to a safe level. And then if you're industry, you take it to the level that you need to say make computer chips. So we call that fit for purpose water treatment. And there's there's been a lot of attention on how to make safe water. And over the last 30 years, the safety of the water in Arizona and the United States has gotten orders of magnitude better. So now, really, I think moving forward, it's really how to make these different tailored waters or fit for purpose water. So if I'm making hydrogen, I need a different quality of water than if I'm making pharmaceuticals or if I'm making, a soda beverage, right? So, we have bottling plants and breweries here. There's one brewery in Arizona that uses reclaimed wastewater, to make a beer, right? So, you can use different types of water. What's in the water sometimes good, like for making beer, but other times you want it to have almost nothing in it. And so, really, I think where the field of water treatment going is more towards this fit for purpose or decentralized treatment. Instead of treating it all to one level in the middle and piping it out, the pipes are getting old, they're expensive to maintain. But, I don't know at home if you have something in your garage, under your sink, in your refrigerator, in a pitcher, right? But you do things because you want certain aesthetics of the water, right? Those aesthetics are different if I feed that water to, or if I don't need those same aesthetics if I'm using the water to take a shower in a hotel as a guest visiting Arizona, right? So each of those need different types of water. So that's really where kind of the water industry is going is fit for purpose water. How things like nanotechnology, other technology can find, kind of its roots there and then kind of expand and grow.
That's a really interesting way, and to see the water future, and I hope that it becomes a more efficient kind of system rather than the centralized system that you were talking about.
Yeah, I mean, there's folks at ASU and trying to just take water out of the air. So even in our building, in our little kitchenette on campus, we have a machine that takes water out of the air in our building and we drink it.
Yeah,
right?
I've heard that. No,
yeah.
That's definitely very interesting.
Yeah.
Can the minus approach or these metamaterials affect the levelized cost of water for clean hydrogen production?
Yeah, so I think, as I mentioned earlier, we have a project from NASA to make hydrogen, and we're using a metamaterial to do that. And we're looking at the effect of water, the things in water, pH, hardness, salinity, on these materials. So what we do is we put a material, a water splitting material, onto an optical fiber, and we put light into this optical fiber, and we make bubbles of hydrogen on the surface. So it's this nanomaterial sits in a metamaterial in this porous optical fiber outer coating, and we can make hydrogen at the same levelized cost as alkaline hydrolysis today. So, this is early phase research, but a lot of, the work on photocatalysis has thought about how to use sunlight, and you're always limited. So we use things like lasers or light emitting diodes, really low cost sources of light to drive these things. And we can do this in all types of water without the adverse benefits that, say, alkaline hydrolysis suffers from using brackish water directly or seawater. So we can do the water splitting with any water quality. And so we have an active project right now trying to compare conventional electrolysis against photolysis or water splitting on the same water, measuring the same metrics in the same ways to really get an understanding of this levelized cost, the effect of your technology selection on what type of water chemistry you need.
Thank you for explaining. So your recent paper, Boosting Hydrogen Production via Water Splitting, an ITO plug, GC3N4 nanomaterial enabled polymer optical fiber design. Sorry for the mouthful. It discusses the challenges of traditional photoreactor designs for hydrogen production using light-driven water splitting, and introduces a novel polymer optical fiber incorporated PEC system. So my question is,
what is that?
Can you explain why traditional designs are less effective and how your new designs could overcome these challenges?
Yeah, so water splitting using light has been around for a while, right? So the easiest incarnation of this is you have a giant bag you fill with water, put in fairy dust and put it out in the sun, and it makes hydrogen. Okay, you need to get the fairy dust out, and it's only good while there's sunlight, right? So people have all different versions of this. Then if you use artificial light, like from light emitting diodes or other sources, and it's usually you would have a glass of water, you put in your fairy dust, you stir it around constantly, you shine light on it, and it makes hydrogen. So again, it's not really this idea of a minus approach. You're still left with a glass of fairy dust and water. And so we've used this approach of attaching these nanomaterials onto polymer fibers. Think of these as like glow sticks at Halloween, right? So they're glowing light. That's from a chemical reaction inside, but we can put light inside the fiber and they glow, just like glow stick or the fancy decorative lighting you see in cars and hotels and airplanes and different things. Those all have a light source at one side, and there's what's called a side emitting optical fiber. These are flexible polymers, kind of like 1 to 3 millimeters in diameter. So they side emit light. The light doesn't have to come through a bag from a sky to hit a material. So then we put the catalyst on the surface. Water's on one side, light is on one side. And so I get super efficient use of the light because every photon is really exciting this nanomaterial on the surface. And so it turns out that process, it doesn't make the material better, it just makes the efficiency of using the light better. So that's that reactor design. And so what we're doing is we're going to take, bundles of these, side emitting fibers, again, bundles of these light sticks, put them in a reactor. I have a lot of surface area because I can put them all together. It's like a cup with lots of pencils in it, right? And it's all the surface is on the outside of the pencil. That's where our catalyst is. We put light from one source onto it. And now we have a reactor with a lot of surface area and a pretty small volume. And this is actually what got NASA really excited because they can bring a small reactor into space to other planets to make things like hydrogen. So this system, photocatalysis, is what we really want. The paper that we published, was like one step. It also had this other step on making it electrically conductive. So it turns out that makes things very complex to build. So we found a new catalyst that's actually better than the one that we published in that paper, and from another partner. But we're able to simplify the system, so we only need light. PEC, which is a photoelectric catalysis, you need light and electrons. So by moving the system to only photocatalysis, it decreases the manufacturing costs, and actually we get about 5 to 10 times better production as well. So, but it all comes back to using a very small amount of catalyst, in this metamaterial on a surface. In fact, we use about 100 times less of this catalyst. And usually these are made up of things like platinum and palladium. So they're costly things. So if I can reduce the reliance on like a lot of that by putting it into this metamaterial, it turns out to reduce the capital cost. And then by using light more efficiently, it reduces the operating cost. And that together brings down this levelized cost of making hydrogen. So we're super convinced we can get to the same costs, as conventional electrolysis, which has been there for decades. We think we can get there to that cost in 2 years, and in a decade be at least 2 times cheaper than that.
Okay. Following up. Oh, and I see that we're at the time. I have a couple more questions for you, if that's okay. Just about 2 minutes.
Okay. Yeah, I thought we were there, but okay.
Oh, sorry. Just to finish this one question was just, what impact could this new system have on the efficiency and scalability of hydrogen production?
So I think in the short term, existing technologies are very scalable, right? So our initial application here is more of a fit for purpose application, just like the other one. And it is NASA, right? So in this case, NASA wants to make a variety of chemicals. It's called in situ resource utilization, in space and beyond. And we're putting these fibers for hydrogen in a reactor where I just switch out the fibers to another fiber, and I can make hydrogen peroxide, or I can do other reactions to make other beneficial resources. So our first market there is more of a NASA application. But we see this, scaling up and taking more time to, mature and be competitive. But in addition to this levelized cost, one of the key things is we use a lot, even then compared to electrolysis, a lot less of these rare earth metals or platinum group metals than traditional electrolysis. So, I think as we think about where these materials come from, globally, geospatially, where they come from, reducing our reliance on these platinum group and rare earth elements is going to be critical. And so, this is true in all green energy applications, from magnets and wind turbines to electrolysis to batteries. And even in this water splitting, we have the opportunity to use a lot less of these, critical materials in this application. So I think it depends upon what happens to the supply chain of some of these materials, how quickly people might switch to these other approaches.
Well, that's very fascinating and promising. If I can just ask you one last final question before you have to leave.
Sure.
In your opinion, how can public awareness and engagement be increased to support the research, development, and adoption of advanced water purification technologies to achieve greater water security?
Yeah, so I think, people understand what water is. And as we started out, that's kind of, you said link it back to things you like. So recently I've been talking to a group, at ASU who does these design studios. And, there's some unifying concepts. And so, and new technologies are going to have to understand this. So Arizona does not have a water problem or a water challenge. In fact, we're really good at one thing. We're really good at evaporating water. So, you sweat. Maybe you don't. Maybe you're special. But, we water lawns, we water trees, everything the problem with water is it evaporates from Arizona, right? So less than 5% of the liquid water that comes into Phoenix leaves as liquid water. So we evaporate everything. So we're really good at evaporating water. So if we get better at engineering the other way, maybe making closed systems. Think of a greenhouse that evaporates water very humid, but if we can capture the water vapor back out of the air, so plants can actually purify the water, because only the water vapor goes into the air, we can reharvest it. So I think the public opinion that we're trying to get across in this new design studio is not to say Arizona has a water problem, but to really get at this fundamental technology. Science is like, water evaporates, right? And there's really cool science there, but everyone understands evaporation. So evaporation is the challenge. And if we can understand how to control evaporation or to reverse evaporation, I think that's really the future of water in places like Arizona.
That's something I haven't heard from anyone else before. So that's definitely a very unique, interesting perspective. I'm excited to learn more about it. So thank you so much for giving me your time. I'm so sorry that we're a little bit over, and I will email you the transcript, and we can talk over email about how this will be published. And I look forward to possibly speaking with you again in the future if you're ever interested in coming back and doing more of this series. We're hoping to continue with this kind of series.
Sure. Hopefully you heard some interesting things in there. Thanks for reading my papers, because you really did read them. That's cool. And you understood them very well. So thank you.
Oh, thank you. Well, they were.
Right.
I could have read more. You have quite the repertoire of papers, and I'm amazed at how prolific your writing is. So thank you so much.
Really good students and researchers in my group. So
thank you so much for taking the time with me, and I look forward to speaking with you further. Thank you.
Bye-bye.
Goodbye.